X is greater than or equal to 0, as is y. Both numbers are greater than or equal to 0. Now, I love when that happens on tests like this because that means that we're allowed to think in terms of numbers that you'd normally think of. We kind of like counting numbers. We like positive integers, that sort of thing. So one way of looking at this problem, not my favorite way, but one way of looking at this problem would be to choose some numbers that work under the constraints of the problem. Since x is greater than or equal to 0, it would be fair to say x equals 2. It would also be fair to say, for instance, that y equals 3. Pick different numbers to make it interesting, and don't pick 0 or 1. Sometimes you can't even pick 2. But I think we'll be okay this time. But say that's what we decide to go with. Well, then, when we try to figure out what quantity a is, the square root of x to the 12th power minus y, well, we'd be talking about the square root of 2 to the 12th power minus 3. And the square root of 2 to the 12th power minus 3, well, 2 to the 12th power, if you go to your GRE calculator and you do 2 times 2, 12 times, you're going to get 4,096. And then if you go to the GRE calculator and you pick, square root button on 4,096, you're going to get 64. So all this, and we have 64 minus 3, which is 61. So how does quantity b compare? Well, here we would have 2 cubed plus the square root of 3. See? Maybe should have picked a number that you can take the square root of really easily. Okay? So that's something that happens sometimes, but we're not sunk yet. We can deal with this. So 2 cubed minus the square root of 3. 2 times 2 times 2 is 8. And 2 times 2 times 2 is 8. Now at this point, what you can do, I suppose, is you can say that you want to do the square root of 3. So you go to your calculator and you hit the square root button while 3 is on the screen. And you find that the square root of 3 is very nearly 1.732 just about, okay? Keep a few decimal points there. 8 plus that times 8 minus that. Alright, and we can say that this is 9.732. And we can say that this is 6.268. And we can multiply these two quantities together. Well, this is 61.00018 or so, according to my calculator. Now, that makes it look a little bit like quantity b is greater, but in reality, this is so small that in all likelihood it's almost as if the calculator is trying to tell us that this quantity is 61 exactly. Well, how do you be sure? This is the situation that you find yourself in when your MO is to plug in random numbers, okay? There definitely was a better number to pick, okay? And if we as test takers are paying a little bit more attention, we may have gone with a 4 in the y position, okay? A 4 in the y position instead of a 3, because we would have noticed the square roots and had figured that, well, we would have had to take a square root eventually, and we know the square root of 4. Why don't we go ahead and attempt this problem with that thinking, okay? So instead of using 3 for y, we'll use 4 for y. And I think that's going to mean that things are going to be a little bit more conclusive for us, okay? So instead of putting a 3 there, we'll put a 4. And remember, we'll have to change this one as well, so I'm just going to write that one over again. Whoops. All right. So this time we have, the square root of 2 to the 12th power minus 4. And we'll recall that the square root of 2 to the 12th power was 64, or recalculate it. and 64 minus 4 is 60. All right, back over here, we're just slotting 4 in. You'll recall that these guys were 8s, but now this is 2, okay? We have the square root of 4, 2. 8 plus 2, 8 minus 2. Well, that means that you've got 10 times 6, and 10 times 6 is 60. See, now I know that what I was thinking about that really tiny decimal part of 61 is in fact true, that they are trying to tell us, or the calculator was trying to tell us in its own naive way, that the two quantities are equal. But now we know for sure because we've picked numbers that are definitely easier to work with. Okay, so that's the plug-and-chug method, okay? And the lesson to learn there is that sometimes if you want to get it done in one shot, you have to take note of things like square roots if you're going to be plugging in numbers. So what's going on as far as the more technical, what I sometimes call the more elegant method? Well, we need to look at the square root of x to the 12th minus y as being something slightly different. We need to recognize that square roots are exponents of 1/2, right? Square roots are 1/2 exponents. That is a rule from algebra, okay? That means that this thing here is in fact x to the 12th to the 1/2 power minus y, no matter what x is, whether it's easy to work with or not. And the next thing I'll remind you of is that exponentiating, let's say, exponents, means multiplying them, okay? Just jotting that down really quick just to put the rule on the screen. But exponentiating exponents means multiplying. This x to the 12 to the 1/2 power is really the same thing as x to the 12 times 1/2. So x to the 6 minus y. This is the simplified form of quantity A. Let's move over to do the simplified form of quantity B and see what happens. We are dealing here with x cubed plus the square root of y, x cubed minus the square root of y. We need to run FOIL. Foiling, multiplying binomials, always a good idea. These are two binomials, okay? And I will write down FOIL and remind you how to do this. First, we multiply the first parts. X cubed times x cubed. When multiplying exponents, we add, well, the value of the exponents. So x cubed times x cubed, or x to the third times x to the third, will be x to the 6th. Now I've taken a cut to throw that rule on the screen just because it's so important, and every time I remember to, I'm going to put it on the screen. This refers to the exponents. Okay, multiply exponents, think adding. Okay, so important. Okay, all of that, and we've taken care of the F part of FOIL. Now on to O. That stands for outer. So we're going to be looking at this guy times this guy, the outermost parts of our two binomials. X cubed times, careful, negative square root of y. That comes across as negative, positive times negative, negative x cubed times the square root of y. And the next thing we have is the I stands for inner. We're going to be looking at those two things. Square root of y, positive, times x cubed, also positive, so we get positive. Again, writing them in the same order as here, we have x cubed square root of y. And finally, L stands for last. We're looking at that and that. And the square root of y times the negative square root of y, careful here, negative, positive times negative, but the square root of something times the square root of something is that thing. Square root of y times square root of y is y. And now what happens here, as always happens when you have a plus and minus the same thing in your binomials, is we have a negative version of this and a positive version of this. Combining like terms means they cancel out. And all we have left after this process is x to the 6 minus y. So we have that, and we have that. No matter what the numbers are, these two quantities algebraically are the same. Okay? Now that kind of took a super long time, but only because I was talking through each and every step. When you get good at this, this is a little bit safer than plugging in, and it's really good to be able to know how to multiply binomials especially, and how to manipulate the rules of exponents and square roots to really break down expressions and simplify them. Here we can see that both these ways of expressing this quantity are equivalent, though they look vastly different. That doesn't appear until you break them all the way down into their simplest forms.